Hello, this is my English speaking practice, and I'm working on coding problems. And right now, I I add comments, English comments to the code. Mm. This problem is the problem I solved previously, and yeah, I have to review English. So in order to have it reviewed by ChatGPT, I will write the English comment. And the problem is this one. Yeah. Copy list with random pointer, and yeah, we should construct a deep copy of the list. We are given the linked list, and the node has next pointer and additionally random pointer like this, and we have to construct a deep copy of the list, so we cannot use the original list. Okay, so we have to create every single node and should update the next pointer and random pointer. That's a problem. Yep, and I've already solved this problem, and right now I'm adding comments. Yep, so let me explain it. The function is copy random list, and it takes head. This is the head of the linked list. Okay, and this might be 0. N is the number of nodes in the linked list. So yeah, it ranges 0 to 1000, and yeah, and if it's none, we will return none. Okay, so we handle edge cases, handle the edge case. If it's none, we will return none, and otherwise we can do it. We can do it with this implementation. Yeah. So the first thing we should do is create a new copy of the head. This should be returned at the end of this function. This is the head of the new linked list. Yep, and this algorithm is can be divided into step 1 and step 2. For the step 1, in the step 1, we are going to create every single node in the copied list, and then we update its random pointer, because it's very difficult to create a new node and updating next pointer and random pointer at the same time, because yeah, when updating random pointer or next pointer, the node that is pointed should be already created. So that's difficult. So there are two steps. Okay, so I should explain this here. This process has two steps. The first one, we we're gonna create new nodes. Okay, create new nodes and yeah, and update its next pointer. As I said, next pointer and random pointer should be updated, but that is difficult. However, the next pointer can be updated at the same time, because next pointer is we can know about the previous node when iterating through the list, so we can update the next field of the previous node. So yeah, we are gonna create new nodes here and update its pointer at the same time. Okay. Yeah, the remaining part is to update a random pointer of the nodes in the copied list. Okay. Update a random pointer. Yeah, this comes from this is because it is not impossible, but it's very difficult to update the random pointer at the same time when we create the node, because when we create a node and try to update a random pointer, the node that is pointed by the random pointer is not always created. So that's the reason why this process has two steps. Okay, to update a random pointer at the same time when we create a node. Yeah, here is the first step. Create new copy of the head, and we keep track previous copied node. Okay, so that we can update the next pointer of it. Okay, and this is used in the second step. Address in original. This is the this is the hash map address of the copied node for the key, and its index for the value. Okay, and this is the no, this is the address of the original node for the key and its index for the value. Okay, because we will want to access the index by the node, by the address of the node. Okay, later. Okay, so that's why it has address and index, and this is the list for list to store addresses of the copied node. And yeah, since this is a list, we can access the node by the index. Okay, and this is the main process, iterating through the original linked list. Okay, and incrementing index and address in original. Yeah, the current is the or already updated, so the current is current point. This car pointer points to the node, original node, so we can use it as a key of address in original, and the value is index. Okay, and we create a new copied node, and at the time we cannot update the next and random pointer. Okay, but yeah, and then address in copied, we push it to address in copied list, and here we can update next pointer of previous copied node. Okay, here is the first step, and after the first step, we already have all of the copied list, and they are connected by next pointer, so they forms linked list already. So the remaining part is to update the random pointer. Yeah, and the problem is how to know the address of the list, because let's think about this node 11, and this is the original one, and when we look at this node and its random pointer points to this. Okay, the value is 1. Okay, but we can't know the index or other information, just know the lists value is 1 and they have next and random pointer. That's it. So how can we know about the copy of this node? Okay. Yeah, because the value could be the same for the other nodes, so the node value cannot be used as an index. So it was difficult. I feel like it was difficult, and so all we can use is index and its address. Okay, so let's imagine we have two linked lists. That is, yeah, the other one is the copy of the original. Okay, so it have same value and same index. Okay, but the address is not the same because the node is not the same. So we have to, so the step is like this. When we look at the node here, we have to update the random pointer of the copied node. Okay, and the random should, in order to update the random pointer, we have to know about the corresponding copied node. Okay, so first look at the random pointer, and the random pointer points some node. Okay, and this node should have index, so we should know its index. So in this case, index would be 0, 1, 2, 3, 4. Yeah, once we know the index, we can access the copied node via index. Okay, yeah, so we can identify the corresponding copied node, so we can update the random pointer. It should point the copied node. Yeah, this is what we do here. And so the current pointer point of the head of the original node, okay, at first, and car random point to the address of the original node. Okay, and if it's not none, we should know about the corresponding copied node. So we can get index, and with index we can get copied node. Okay, and update the random pointer of node I in copied list. So the current node, this is node, should be updated, and the random pointer is copied node. Yeah, if address is none, we just update it to none, so it's okay, and move on to the next, like this. That's all. Okay, so have it reviewed. First, handle the edge case. This process has two steps. Step 1 is to create all the new nodes and set their next pointers. Step 2, set the random pointers for each node in the copy list we separate these two steps because it's hard to correctly set the random pointer while we are still creating the nodes. Still creating the nodes. Yeah, create a new copy of the head node, keep track. Yep. I prefer this version. Alright, so first off, if the list is empty, we just return none, and we are gonna do this in two steps. Step 1 is to make a copy of every node and set up all the next pointers. Step 2 is once we have the structure ready, we'll come back and fill in all the random pointers. It's just easier to think about this way because setting random at the same time would get messy. Setting random at the same time would get messy. Yeah, so let's start it by copying the head node, okay? And we'll keep track of the previous copied node so we can connect the next pointer properly as we go, okay? And we also need to remember which original node maps to which copied node. So we will keep two data structures, one dict for original to index, and the one list for index to copied node. Now we just walk through the original list and build a copy. Create a new copied node here and connect it with the previous copied node and move forward in both lists. Okay, so now every node is copied and connected by next field. The only thing left is the random pointers. Let's find which node this random pointer should point to. Okay, and now we can update the random pointer of the copied node, move on to the next node, and that's it. The list is fully copied. Okay, great work. So let's move on to the next problem. Linked list cycle 2. Easy one. There is an easy one. Okay. Given the head of the linked list, return the node where the cycle begins. If there is no cycle, return no. There is a cycle in a linked list if there is some node in the linked list that can be reached again by continuously following the next pointer. Internally, pos is used to donate the index of the node that tail's next pointer is connected to. It is -1 if there is no cycle. Note that pos is not passed as a parameter. Internally, pos is used to donate the index of the node. What? Tail's next pointer is connected to. I see, but pos is not passed as a parameter, so why do you mention to pos? I don't know. And there is a follow-up question. Can you solve it using constant memory? Okay, so we don't use extra we don't allocate new arrays, or yeah, like that. We just use only extra constant space. And the constraints is like this. The number of the nodes in the list is range 0 to 10 power 4. Could be none. Okay. First of all, we should handle edge cases, and node value is like this, and pos is there is no cycle or a valid index in the linked list. Okay. So yeah, to find the cycle, we have 2 pointers, and that they are slow one and fast one. Okay, and they move forward at a different pace. So if there is a cycle, the first pointer will reach the slow pointer. Does it make sense? So we can find the cycle, but the problem asks us to return the node where the cycle begins. Okay, so yeah, we should think about this. And with constant memory. So we will use double pointers to walk through the linked list. If we can use hash map or set, we will store the address of the nodes we've already visited, and yeah, if the first pointer should visit twice for the first time, the first pointer should visit the same node twice, and we can identify the node where the cycle begins. Yep. But we cannot use the set. Yeah, because follow-up question requires us to not to use set. So we have to find it without storing the addresses of the node we've already visited. Mm. Hmm. 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 Let me code it with. Let me code naive solution. Can we use set to store addresses? So bstit should be initialized like this, and we are working through the linked list at a different pace. Slow, fast, head, and while fast exists and fast next exists, we can oh sorry, slow and fast. Head to next. Sorry. Head to next is none. Next is none. I'm not sure this the edge case or not. Anyway, we initialize slow and fast pointer like this, and as long as fast and fast dot next exists, yeah, we have to compare slow points to fast. It's same. There is a cycle, and there is a cycle, if they are not the same, move forward. Move forward and move forward. Yep. Yep. And visit it. At if as is none and first next is already in the visited set, the answer is the node where the cycle begins is first next. Return answer. If there is no cycle, yeah, if there is no cycle, answer must be none. Yeah, so we just return none. How about this? Wrong answer. This case. Yeah, makes sense. This is kind of edge cases. Because it starts with head and head next. So really. Okay. but we have to remove this one according to follow-up question. Before thinking about this, let me submit this one. Oh, wrong answer. There's one. It is a self cycle. Self cycle is good. How can we remove? How can I? This set. I see. I come up with solution. When we get when the fast pointer and slow pointer points the same node, we start to walk a cycle again, right? And we have to store the address of the node. Okay, and when it's not good. This is wrong. Yeah. I'm good. And so once we remember the address of the node, we can we can get the length of the cycle, right? Because in this case, going 1, going 2, going 3. So the cycle consists of 3 nodes. So but how can we the end of the node? Let me see. Hi. Yeah. Uh, Difficult to explain, but let me. Fast, slow, and fast. So first met address of the first met would be the like this, and it should break, and we left and right one should be initialized like this, okay? And okay, right next is not first met. Left would be left next. Right would be right next. Oh, if first met is none, there is no cycle, so return none. And from this, there must be a cycle, so we are going for one cycle, okay? So this case, yeah. So what we want to do is it's too small. Let me think about 1, 2, 3, 4, 5, 6, 7, and there is a cycle. Okay, and the first met would be, I don't know, 5 or 6 or 7. Okay, and we want to find this one. Hmm? Hmm? Yeah. So, for example, the first met is 7, and the cycle is moving once, twice, 3 times. It means there is three nodes. 3 nodes consists a cycle. Okay, so when we start from left one, the left pointer would point here. Okay, and we are going next to iterate, and this one, when this point the end of the linked list, this point should point the start of the cycle. Okay, but I realized we cannot know about the end of the linked list, so that is not good. So we can know how many nodes consist of the cycle. Okay. And the cycle contains end of the node, but we cannot know the end of the linked list. So that's a problem. First met is not important. Yeah, we want to know. I see. But this is not efficient, but I come up with the idea. This case, next would be the node itself. It points the same node. Okay, so we checking for each node. In this case, we can know the cycle consists of 3 nodes, so we check next of next of next. In this case, next is not same, so 1 is not good, and 2 is also not good, 3 is also not good, 4 is not good. And when we look at 5, next is the node itself, it's same. So the first node where begin cycle is this node. Okay, but this is not efficient because node number for each node. But it's okay. When the cycle is large, we can find the node where begin circle in the early part in the linked list, because cycle is big. And when the cycle is small, it would be late in the linked list, but the cycle is small, so it doesn't take time for one checking. So this case 1 2, so we count plus 1 2 3 and yep. And when they are the same, it's the beginning of a cycle. So the cycle consists of 3 nodes. Count would be 3, so we start with 3, going next once, twice, two, 3 2 2 2 2 1 1 2 0. Yes. And otherwise oh 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 one pos is 0 1 2 3. Oh speed is not good, but the memory is great. But this is so simple. Slow and it's fine. Found is true. Hmm? Really? Maybe I miss some point. Move the slow pointer one step and the fast pointer 2 steps at a time through the linked list until they either meet or the first pointer reaches the end of the list. Yep. If the pointer meets, there is a cycle in a linked list. Reset the slow pointer to the head of the linked list and move both pointer one step at a time until they meet again. The node where they meet is starting point to cycle. Really? Really? One, two, 2 4 3 6 4 8, but 8 is not. So 4 5 5 7 6 6. They meet at 6. Okay, and the slow pointer is moved to 1 and going 1 by 1. 2 7 3 5 4 6 5 7 6 5 5. They don't meet forever. Move both pointers one step at a time. Can we make sure they meet again? I don't know. 1 6 2 7 3 5 4 6 5 7 6 5 7 6 7 5. No, 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 no. I don't understand. I cannot understand. The algorithm works by using 2 pointers, a throw pointer and a fast pointer. Initially, both pointers are set to the head of the linked list. The first pointer moves twice as fast as the thrower pointer. If there is a cycle in the linked list, eventually the first pointer will catch up with smaller throw pointer. If there is no cycle, the first pointer will reach the end of the linked list. Okay. When the 2 pointers meet, we know that there is a cycle in the linked list. We then reset the throw pointer to the head of the linked list and move both pointers at the same pace, one step at a time until they meet again. Can we make sure they meet again? The node whether they meet is the starting point of the cycle. If there is no cycle in the linked list, the algorithm will return null. Let's say we have a linked list with a cycle like the one below. To detect the cycle and find the starting point, we use 2 pointers, a throw pointer and fast pointer initially set to the head of a linked list. Then we move the pointer through the linked list. The throw pointer moves one step at a time, while the fast pointer moves 2 steps at a time. Starting here. So 2 3 3 5 4 4 7 5 6 6 7 7 6 5 5. Oh, they meet 5. Okay, so 5 1 5 2 6 3 7 4 5 5 6. They don't meet. 1 5. They start at 1 5 2 6 3 7. Okay, 4 5. They don't meet. Sorry, I missed. So 1 2 3 3 5 4 7 and throw it first. Yeah, no. it's because in the first while loop, the first pointer is still at the node where the throw met it. Now we've only reset the throw pointer back to the head. First is at the last position and then throw. Next and first. Next will move. Oh, this one is. One can assume it as a trait of list with a cycle. Imagine you have only cycle, say third node point to the first. Okay? If one pointer does one step and the other does two steps, they will meet in the first point. When the slow one makes one lap and the fast one makes two. Hope you imagine this case they cannot meet earlier and they for sure will meet at the starting point. Now the feature is that the steps could before cycle start from beginning. X steps before cycle, Y steps from cycle. Start the meeting points. Distance traveled by throw a pointer before meeting X plus Y. The default distance traveled by first. What is X? What is Y? Before cycle is X. Cycle starts to the meeting point. Let's assume they meet at 6 and Z steps from the meeting point to the cycle starts. So this start at 6, so and end at 5, 2. Okay, throw pointer distance two, 3, 3, 5, 4, 7. Five, 6, 5 7 7. So y is like this. They meet at 7, okay? And z steps from meeting point to cycle start. That is 7 to 5. One, two, three, 4, 4, 2, 4, 2, 1. Slower pointer is, for example, this case 1, 2, 3, 4, 5, 6. Okay, now faster pointer should be 12. And x plus y. Yeah, must be slower pointer. Distance of the slower pointer. Makes sense. And faster pointer is x plus y and y plus z. X plus y plus z plus y. Why like this? Before cycle and cycle starts to meeting point and I see. So I understand this equation, and x equals z. I understand. This is cool. This is cool. Detect linked list cycle 2. Oh, I didn't create a file. Linked list cycle 2. But my solution is not bad because it's just 10 milliseconds later, so not bad, and memory is good. Oh. Anyway, move on to the next. How many problems today I solved? three problem. Hmm. 20, yeah. I have to until 85 for this week. Okay. You are given the head of a singly linked list. The list can be represented as reorder the list to be on the following form: 0, n1, n-1, 2, n-2. Okay, you may not modify the values in the list nodes. Only nodes themselves may be changed. Okay, gotcha. Okay, I see. Reorder the list. So n-1, 0 to n. Okay, 0 to n. Points. Points. Yeah. Maybe. Oh, but not modify the values, so we can. Yeah, of course we can update next field, next pointer. We should update. So 1, 2, 3. Okay, we want to move forward two direction from start moving forward and from the end moving backward. Yeah, and the direction would change at the middle point. So we going with 2 pointers, fast and slow. It's because we want to find the middle point of the list. So going fast and going slow, and when the fast pointer reaches to the end, the slow pointer should point to the middle of the node. Okay, and then we are the slow pointer moving forward and update the next pointer to the previous node. Okay, and 2 points to 1 point to 2, 2 point to 3, and 3 point whatever, and 4.3 and 5.4. Okay, so they are heading to the middle. Okay, and also we have we prepare 2 pointers, left side and right side, and they are going forward, heading middle, and then we are going to update their next pointer. One should point the node that is pointed by the right node, okay, and going to moving forward the left pointer, moving the left pointer forward, and for right pointer should point the node that is pointed by the left pointer, okay, and moving the right pointer to this direction, okay. That's all. Let me I want to solve this problem quickly, so can I use this? So the first step is slow and fast. Slow, fast, head, while, fast, and fast. Next exists. Slow is move one step at a time. Fast is move 2 steps at a time, okay. When this condition doesn't meet, the slow should point the middle node of the linked list, and then we are updating the next pointer for second half of the linked list, okay. So that means while slow believe is none. If believe no slow temp is slow next, okay, and slow next. If believe slow next would be believe, and finally move on to the next. Slow should be temp, okay, yeah. And for the final phase, left and right, we have left and right pointers. Left should be head, right is end of the list. So slow, prev, yeah, prev must be end of the list, I think. Yep. We don't need to store the middle node. Left and right, left and right, left and right, left and right. While left, while not left equal to right. The next point left. Start from left. Left, right, left, right. Yeah. Left point. Left. So temp left. Next. We can update left. Next. Left next pointer points the right node. Okay, and after updating left, moving forward to right, like this, and after that if left break, temp is right next. Okay, right next should be left. Okay, and after updated right is temp. That's all. Return. Left and right. Yeah. And believe is slow. Let's go. Takes a long time. Something wrong. Memory limit exceeded. Really? Memory limit? I just use pointers. Really? Look for the middle point, and from the middle point we want to update the next pointer. Slow right. Not bad. memory limit exceeded. Really? Is this not good? I don't know. Interesting. Oh my gosh. Okay. 1, 2. 1, 2, and 1, 2. Yeah. And while throw. Why? Slows next. Wrong. Okay. But this is the address, right? Is slows next. Throws next previous. I don't know. Throw. Three, 4, 4. Throw is 3. Throws next is 4. Tempo is 4. Wet. Three, 4, 4. Slow is 3. Slow's next is 4. There is no brief. So the first time. This is good. Brief is now. Brief is now. What is this? Brave. This is not good. Hmm? I don't know. I have no idea. Eh? There's no infinite loop, but the memory limit exceeded. Oh, I'm really. Huh? Huh? I cannot understand this situation. Leave is not done. Hmm. Okay. memory limit exceeded. Time limit exceeded. Oh, so that is time limit. Okay, the error message changed. We'll get this one. Memory limit exceeded. debug it. Okay, let me run programs. Reorder list. The test cases is we have to start index. List node. Each 1, 2, 3, 4. And reorder list. Three, 4. Three, 4. 3, 4. Yeah. maybe I didn't update the next field of the end node, so that might cause the memory limit exceeded, because I don't know how they check the code. It must refer to this one, and if they have a cycle, yeah, it might cause the memory limit exceeded. So the problem is that I didn't update the next field for end node. How can for example, the throw point 3 and 4. Three. So how to identify the end of the node? 1, 2 and 3, 3 and 5. Okay. So maybe great, improved. The left and right, right is sleep. 1524, 1524. Oh. So this point too. Now, okay. Mm? Mm. If right. But it's same. Maybe this cause memory limit exceeded. Yeah. Makes sense. 1 2 3 4. Really? My should be like this. 1 2 3 4 2 3. 1 2 3 4. Really slow. 4 5 4 5 4 5. That's good. So the one, two, three, four. 1 2 3 4. 1 2 3. 3 shouldn't. I see. This is the current as is to be. Okay, that's why there are that's why 1 5 2 4 3 4. Yeah, infinite linked list. That's why. So we have to identify the four, 5, 3, 4. Okay. Okay, I will do it. While first and is move 2 steps at a time. Okay, and 1 2 3 4 1 2 3 4 5 2 3 So while fast, no, slow, update, slow, and slow is updated to slow next. But I already implemented like this. Yeah. Is true. Okay. Five. Next is D. Next is A. Three is true. 3 is true. Great, great, great. Great. Mm. Great. Great work. One, 4, 2, 3. Great. Great, great, great. Oh. Oh. I don't know why I took a so long time to fix the bugs. Okay. Yeah, I wanted to solve this quickly. Give me one more chance. Insertion sort. I solved this problem within 10 minutes until 28 p.m. Given the head of a single list, sort the list using insertion sort and return the solid list head. The steps of the insertion sort algorithm. First, insertion sort iterates, consuming one input element each repetition and growing a sort output list. At each iteration, insertion sort removes one element from the input data, finds the location it belongs within the solid list, and inserts it there. It repeats until no input elements remaining. The following is a graphical example of the insertion sort algorithm. The partially solid list initially contains only the first element in the list. One element red is removed from the input. Partially sorted list, remove it and insert it. It's good. Yeah. Okay. Okay, there's no constraints about space complexity. So insertion, sort list, insertion sort list. Okay. Partially sorted list. Call head car. Okay. While car. And the head might be, no, head must exist. Head next. So while, after while loop, we return solid list. Okay, and we are looking at the current node, and we should compare insert, yeah. Name. Start with sorted list. Insert while sorted list is greater than car value. We going to next. Okay. If none, not good. If the next pointer is none, prev next would be car, okay, and break. And we need pivot. Sorted list. Pivot next. Pivot next would be the head. Okay. Head. And the prev start with pivot and so we have prev and p, and p value prev next would be car. Car next be P. Okay. That's it. And finally we move on to the next loop. Yep. And we return car pivot next. Yep. Sorted list. I don't know. Time limit exceeded. Okay. Why? Why? 4213. 4, 2. With pivot. Piece 4. And current is 2, so cannot do this while loop. Prev next would be car. Car next would be P. Two, four. Yeah. Ah. I understand. How about this? 2, 4. at current, and the P is maybe should be none, and oh, time limit exceeded. Okay. Great, not bad. So let me explain it. We want to return the head of sorted list. So, but the head of sorted list might be changed every time we insert a new element into the sorted list. So we want fixed something fixed. So we call it pivot. That's like a dummy node, and dummy node point to the head of the sorted list. And at first, the head of the sorted list is also head of the original list. Okay, and the important thing here is we make a partially sorted list, and the end of the node of the list should be disconnected to the current original linked list. So we disconnect here like this. Okay. Yeah, because if we don't do this, when inserting a new sort, we end up with working through the end of the original node. So that's not good. The partially sorted list, we make sure the length of the partially sorted list, and so we disconnect it here, and this is the main process. As we can see, we have to look at the element one by one. So the current pointer points to the yeah, one element. Okay, and prev and p, that they point to the previous sorted list, partially sorted list. And prev start with pivots. Yeah, it's most prev is start with pivot. Okay, and the p is the next node to the pivot. Okay, we point to two nodes. Okay, and we compare p and current node, because p should be partially sorted. Since they are partially sorted, so p is start from smaller one, and if the current value is larger than p, we can move pointer forward, prev and p. Prev is gonna be p, and p is gonna be p's next. Okay, and here is the edge case. If the p is none, so it means partially sorted list reach to the end, we can update the previous next to the current node and break the while loop, because we can append it to the end of the partially sorted list. And after that, previous next gonna be current. Yeah, in this case it's redundant, but yeah, it's not affect, it doesn't affect battery, so yeah, we don't care about this case. For normal case, we have prev and p, prev node and p node, and the current node must be between them. So prev next gonna be current, and current next point to p. Okay, and in order to move forward the current node, before update the next field, we use temporary variables like this, and we move on to the next. Yeah, and finally we just return pivot next, because pivot always point to the head of the sorted list. Yeah, that's all. Okay, so it takes 20 minutes. Let me solve one more. Given the head of a linked list, return the list after sorting it in ascending order. Okay, just sorting it. And can you sort the linked list in n log n time and O1 memory? Okay. Interesting. Linked list. Okay. N log n. So we have to divide it into two parts and sort it for each, and then merge it. The divide and merging. N times log n times log n. Yes. It can be. It's like a merge sort. But but how to access the middle? We have to use characteristic feature of the linked list. Partially sorted. Can we merge with linear algorithm? -1 and 4, -1 and 3. So 3 and compare 4 and 5. 4, okay. 4 compare 5. Oh, sorry, 0, 4. So let's take a look at pivot takes -1. -1 takes 3 or 0, and 0 takes 3 or 4, takes 3. 3 takes 4, 4 takes 5. Yeah, merge can be done with linear algorithm. So merging is not difficult. So the problem is halves, divide and conquer. Divide, merge. Okay, we want to divide it evenly. Divide it into two parts. So we use 2 pointers, slow and fast, head, while fast and fast next. Slow, move 1 steps, fast, move 2 steps at a time, and slow gonna be point to the middle. Divide takes list node, Mm. Believe is now and slow. Yeah. Believe next. We have to disconnect the first half and second half. And we return slow. Okay. Yep. So sort list. It looks like recursive. It looks like recursive. Can be solved by recursive function, I think. And it takes list node, and here is a base case. If node next can be none, so in this case we just return node as a sorted list of as a head of sorted list, and this case we have to swap them. So the A next gonna be node next is the end. Here's a base case, so we can handle a single node and double node. Okay, if there are three or more nodes exists, we have to divide we have to divide and first head is node, okay, and then they are divided sorted second head and first sorted first head is, yeah, first head, okay, and after that we merge it, we merge okay, and return head, okay, and merge is like head 1 head 2 I already simulated create a list node and left pointer and right pointer, 2 pointer, anyway there is 2 pointers, head 1 and head 2. So or the current is pivot. Head 2 if next head 1 and if head 1 value is less than head 2 value, we choose head 1. Okay, otherwise we choose head 2. Okay, and why? Why this the one is none? Might be true, because I don't know. We have to, when we use head 2, when we use head 1, go next, head 1, head 2 next, return pivot. Why? I'm not sure. Pivot to next. I'm not sure. I believe this is a bug in language server. My code is not bad. We can merge it. Let's go. Runtime objects. Where it is. This one. Node might be. Really? Let's go. Wrong answer 4. Just return 4. I see. But this is not real problem. The problem is Okay, I see. Seems good. Great. Not bad. Okay, so let me explain how it works. First, if the head is none, we'll return none because we have nothing to do, and we are building like a merge sort. Yeah, it's yeah, the main process is this function rec. This stands for recursive function. Yeah, and this function plays a role to sort the list. Okay, so when the node when it takes a single node, it just return node because we don't need to sort anymore. We just return the node, and in this case there is just two nodes, so it's easy, so we can do it within this function. We just compare the node and the next node, and if the first one is larger than the second one, we swap those nodes and return the head of the sorted list. Okay, this is the base case. Yeah, and when the number of nodes is 3 or more, we have to divide and solve it recursively, right? So we divide it into two parts, and the divide function is like this. It can find the middle of the linked list. Yeah, we use two pointers, and the first pointer move two steps at a time, and slow pointer move one step at a time. So when the first pointer reach to the end, the slow pointer must point to the middle node of the linked list. And additionally, we have to disconnect the linked list. So yeah, this function is divide. So the prev pointer point to the just one before middle node. Prev pointer point to the node just before the middle node. Yeah, so the next field should be updated to none. Yeah, it means disconnect it and divide two part. Okay, and this function returns the head of the second half. Okay, and head of the first half is obviously the node. Yeah, because this function takes the head of the linked list. Okay, so we can use it. Okay, and after that we solve the same problem for each part. As I said, this function can sort it. So we just pass the head node for each, and we can get the sorted second head and sorted linked list, and this point to the head of each list. Okay. Yeah, this structure maybe not easy to understand, but this function can solve the can sort it, so we can use it. Yeah. And finally we have to merge sorted list. Okay, so yeah, if we get the linked list like this, first we can divide the two parts, and based on the implementation, the divide is like first like this, okay, and after divide it, we can solve the same problem. How about this? This is just two nodes, so we can solve this directly. Just compare with it, and -1 and 5, that is already sorted, so this is like this, and this one is have to be divided, so it's divided like this. And another step, for the next step, 3 is 3, and this part can be solved, just swapping. Yeah. And yeah, we can get sorted list. So from now we are merging. So 3 and 0, we choose 0, and 3 and 4, we choose 3 and 4. Okay, and finally merge this. This is -1 and 0, we choose -1 and 0 and 3 and 4 and 5. Yeah, we can get it sorted, and the time complexity is divide is linear, and but it calls recursively function, but this divide two part, so we can it's logarithmic algorithm, so how can I say, divided by 2 and repeat it, it's logarithmic, so log n, and for each recursion we have to use divide and merge. This is linear algorithm, so overall the algorithm is n log n. Okay, and we don't use any extra space, so the space complexity is constant. Yep. Yeah. That's it. Okay, I solved 5 problems today. Yeah, I will finish today. Thank you for watching.